Hey, you're driving a car. On the way to the grocery store, but then you need to take a turn. You're thinking to yourself, what is the maximum velocity my car should have? Alright, back to basics. Do you remember those little basketball toys that were attached to your wrist via a string? They were like really popular during the early 2010s. Let's say you want to spin the ball with uniform circular motion. By doing so, there's going to be a centripetal force, as well as a centripetal acceleration pointing towards the center at all times. The acceleration also points towards the center, since acceleration in general always points towards the same direction as the net force. The velocity of a ball, on the other hand, is tangent to the path of a circle and perpendicular to the radius. We therefore call it the tangential velocity. Besides the tangential velocity, we also have the angular velocity. You ever been on those circular playground things? If we have two persons sitting on it, one near the center and one near the edge, and we let them spin, then you can see that the angular velocity is the same. They both finish one revolution at the same time. However, the one sitting at the edge covered a lot more distance, which is why his tangential velocity is higher. That's why you should always stay there at the center on these rotating things in order to win. Now, since we talk about revolutions, let's talk about the period. If it takes a person 2 seconds to complete one revolution, then the period would be 2 seconds. The frequency, on the other hand, tells us how many revolutions are being made in a second and is measured in hertz. So due to the period being 2, the frequency must be 1/2 hertz. Many people think that the centripetal force is a force like gravity. However, that's not the case. It's basically just a net force which points towards the center. So if you were in space, for instance, then the centripetal force would resemble gravity. And if you are spinning a ball, it would be tension. Besides the centripetal force, you probably also heard of the centrifugal force before. When you're in a car which is taking a turn, you usually get pressed to the side, which points opposite to the direction you took a turn towards. Most people think that the centrifugal force is the reason this happens. But fun fact, the centrifugal force is not real. The reason why this happens is due to inertia, which we discussed in our last video. Inertia tells us that an object moving in a straight line is going to continue moving in a straight line unless a force acts on it. So it basically wants the object to move out of the circle in our case. I mean, if you spin a ball attached to a string really fast and you loosen the grip, the ball is going to fly away due to inertia overcoming the centripetal force. Alright, let's look at the remaining equations. These are the most important ones regarding uniform circular motion. Okay, most of you are probably familiar with this. 2 pi r tells us the circumference of a circle. If you didn't know that, don't worry buddy, I hated geometry too. But if you think about it, this equation makes a lot of sense. The total distance this object travels here is 1 revolution, which is the circumference of a circle. And the time that it takes to complete the circle is just a period. So if the radius is 1 and the period is 2, then the ball traveled pi meters per second. Since the period is equal to 1 over the frequency, we can also rewrite this to 2 pi r times the frequency. The angular velocity shows us how fast the angle is changing. Due to 2 pi being 360 degrees, we get 2 pi over the period, or 2 pi times the frequency. Now let's look at the acceleration. The acceleration is equal to the velocity squared over the radius. The higher the velocity, the higher the acceleration. The higher the radius, the lesser the acceleration. I know that your hand might be hurting by now, but try to spin a ball again. If you spin the ball with a constant speed while shortening the string, then you feel the string pulling harder on your fingers due to an increase in acceleration. Okay, now we should be ready for our car problem. Since you are a nerd, you know that the radius of a circle is 80 meters. And the coefficient of friction between the tires and the road is about 1/2. Alright, the first thing to do is to look at the free body diagrams. The weight points downward, the normal force points upward, the drive force points towards the same direction as the tangential velocity, and the resistive forces, like air resistance for instance, push the car back. The force of static friction, on the other hand, points towards the center. That's our centripetal force. Due to the car laying on the ground, the sum of the vertical forces have to be zero. The static friction force is equal or less than the coefficient of friction times the normal force of a car. But why is that the case? Let's say we are trying to push a heavy box on the ground. By doing so, the static friction is trying to prevent us from achieving that. However, if we are pushing hard enough, which means that our pushing force is higher than the maximum threshold of the box in our terms, then the box begins to move. Which is why the static friction force can only be less or equal than the coefficient of friction times the normal force. Now in this case, the box was at rest in the beginning, so why are we using the force of static friction in our example? I mean, the car is moving already, right? Well, the force of static friction works to prevent slipping, whether it's stopping the box from slipping forward or preventing the car from slipping outward in a turn. So, at any moment, static friction acts in response to the applied forces, trying to cause relative motion between the surfaces. In our case, it's the tires and the road. Due to the force of friction being our centripetal force, we can rewrite this as ma is less or equal to the coefficient of friction times the weight, according to Newton's second law, and get rid of the mass. So as we discussed before, the centripetal acceleration is just the velocity squared over the radius. Now solve for the velocity to get the velocity squared. Now we take the square root, and by plugging in the values 1 over 2 times 10 times 80, we get about 20 meters per second. So the car must not travel faster than 20 meters per second, which is roughly about 72 kilometers per hour, or 44.7 miles per hour in freedom units. I also did a full summary about uniform circular motion on Notability. You can follow me there, it's completely free, and if you use GoodNotes then you can just download the PDF, it's in the video description. This video took a lot of work, so I would happily accept new subscribers as payment.